This is the second video for the further kinematics final mechanics topic. And in this, we're going to look at how we can use our constant acceleration formulae, our Ch8 formulae, but with vectors. And this leads to, you're very familiar with calling them Ch8, but we can actually, because we're now using, instead of displacement, we're using position vat. And we usually just use of the ones that we've seen. So V equals U plus A, and on your notes you see that. But this time, instead of using the one that we use quite frequently, which is S equals UT plus a half AT squared, I'm just writing that, we use R equals UT plus a half AT squared, because our displacement is actually a position vector. Okay, but again, you've got to be very, very careful. So you can see that R is the displacement at time t, U is the initial velocity, V is your vector velocity, at time t, and A is your acceleration. And these three things, R, U, V, and A, are vectors. The only scalar quantity in there is t. So let's have a little look, and this is example 4. So I'll have a little look at this one. So it says, a particle P has a velocity negative 3I plus j meters per second at time t0. The particle moves with constant acceleration A, which is 2I plus 3j meters per second. Find the speed of the particle and the bearing on which it's travelling at time t equals 3 seconds. So if you think about it, all right, we've got this particle. It's moving with a constant acceleration. Okay, so for this one, I'm going to work in column vectors. Okay, so I'm going to write down my information. So don't forget that this is your initial velocity. So U equals negative 3, 1. It has an acceleration of 2, 3. Our time is 3, and I want the velocity. Okay, well actually what I want is the speed, but before I can find the speed, because of course that's the magnitude of velocity, I need to find my velocity. So I'm going to quote my formula. So V equals U plus AT, one of our standard Ch8 or Ch8 in this case, because we're dealing with vectors. Okay, so V equals, so it's negative 3, 1, plus, and I'm going to put the time first, so it's 3 lots acceleration. Okay, so if I work that out, negative 3 plus 3 lots of 2, negative 3 plus 6 is 3, and 1 plus 3 lots of 3 is 10. So that tells me my velocity when t equals 3. Now it does ask for the speed, so I'm just going to draw a little diagram. So there's my speed. So again, so it goes 3 across and 10 up. So there's my velocity triangle. Okay, so my speed. So the speed, and we use good old Pythagoras, is the square root 3 squared plus 10 squared, which of course is root 109, which is 10.4 meters per second. So that's the speed it's going at when t equals 3. And of course I can use my little diagram that I have here to find angle. Now don't forget, it's actually said the bearing, so I'm going to find alpha first, and then I'm going to find my bearing. So remember, alpha is inverse tan, or tan to the minus 1, of opposite over adjacent. Okay, so alpha equals, okay, that comes out as 73.3 degrees. Now don't forget a bearing, and I'll write it on this diagram in red. A bearing is taken from north clockwise. So therefore, my bearing, well, to calculate that, I would do 90 minus 73.3, and then remember it is a 3-figure bearing, so it's 0, 1, 7. Okay, so hopefully you're happy with that one. Now, the next question is a context question, so let's read it together. Okay, so it says, an ice skater is skating on a large flat ice rink. At time t equals 0, the skater is at a fixed point 0 and is travelling with a velocity 2.4 I minus 0.6 j. At time t equals 20 seconds, the skater is travelling with a velocity of negative 5.6 I plus 3.4 j meters per second. Relative to the origin, the skater has a position vector s at time t seconds. So modelling the skater as a particle with constant acceleration, we're going to first of all find that acceleration. Now, okay, so the first thing we're going to do, and I'm going to work in column vectors. Okay, so I've got V equals, I'm going to change my vectors into columns. So it's U plus AT, one of our standard supermats. So the velocity that they are travelling at, okay, a final velocity, remember this is final, this is their initial up here. So their final velocity is negative 5.6, 3.4 equals their initial velocity, which was 2.4, negative 0.6, okay, plus acceleration, we don't know, but we do know at time 20, so let's say 20a. If we rearrange that, okay, we get that 20a equals, well, it's going to be negative 5.6 minus another 2.4, which is negative 8, and 3.4 plus 0.6 is 4, therefore a, and all you have to do is divide by 20, so you get negative 0.4 and 0.2 meters per second. Or you can write that in i's and j's, so that's negative 0.4 I plus 0.2 j, and that is also meters per second. Okay. Now, the next bit says find an expression for s in terms of t. So we're using s. Notice it's bold, so it's not displacement, it's actually position vector. So this time again we're going to use our standard suvat s equals ut plus a half at squared, remembering that s, u and a are vectors and t is scalar. So, okay, so s equals, okay, so I want u, it's 2.4 and negative 0.6 t plus a half. Now I've just found my acceleration, so it's negative 0.4, 0.2 t squared. Now what I'm now going to do is, just sort that out a little bit. So I get s equals, okay, so 2.4 negative 0.6 t, and then it's plus, and I'm going to put this in here, negative 0.2 and 0.1 t squared. Okay, or you can pull it together. Okay, or you can have s equals, and you can pull it together as one big column vector, 2.4 t minus 0.2 t squared, negative 0.6 0.1 t squared. You can also therefore write it in i's and j's if you want to, and I'll write that. S would equal, and it will be 2.4t minus 0.2 t squared I, okay, plus, and then negative 0.6 plus 0.1 t squared j. Completely up to you how you write it. Now, part C says, and we're going to use that answer, it says, find the time at which the skater is directly northeast of the origin. Now, there's the origin. If the skater is northeast of the origin, look there, they must be somewhere along that line, a line that runs at 45 degrees. And therefore, you know, if you look, if you're running at 45 degrees, the x and the y will be the same. So either the x components and the y components will be the same, or the I components and the j components will be the same. Okay, I just realised I've missed a little t off there. That's because I don't particularly like. Oops. Still there as well. Okay, sorry about that. Okay, so we're going to put our x and y components together and equal to each other. All right, so if they are, then Sx must equal Sy, or the I components must equal the j components. So therefore, 2.4t minus 0.2t squared must equal minus 0.6t plus 0.1 t squared, and therefore you're going to solve that. So we just want to rearrange it. If I rearrange it, I end up with 0.3 t squared minus 3t equals 0. You can pull out t as a common factor, so you get 0.3t minus 3 equals 0. Therefore you get t equals 0. Well, that's logical because that's at the start. Okay, or t equals 10 seconds. Okay, if you set, highlight that one. So if you set this equal to 0, and therefore add 3 and divide by 0.3, you get your 10. So, okay. So in other words, this skater is directly northeast of the origin when t is 10 seconds. Okay. Now, it then says a second skater travels to show that she has a position vector r equals 1.1t minus j. You can see that because we've got two skaters, okay, we've used the r for the second one. Okay, so we used s for the first one and r for the second one. All right, so, okay. Now, if you look at that vector, you'll notice that there is no I component. That means that the second skater is actually travelling in the y direction at some time t. They're on the equivalent of the y-axis. Now, if you think about this, you're looking down on the ice. So they're travelling from the origin, they're travelling straight up in the just in the j direction, and so in the y direction. So you've got to show that the two skaters will meet. Okay, so I'm going to write the position vector of skater number 2. So here I'm going none in the x direction, in the I direction, and 1.1 t minus 6 in the j direction or in the y direction. So we're going to compare that with s from part B. Okay, so we're going to look at either the x's or the i's and the y's or the j's. So we'll look at the x components. Okay, so what you've got is 2.4t minus 0.2t squared equals 0. Okay, looks like a quadratic to me, so we're going to solve that. So we're going to away t as a common factor. So we get 2.4 minus 0.2t equals 0. Now, I'm doing this because it says show that. So, okay, that's t is 0, or, okay, t comes out as 12 seconds. Okay, that's the x's. Now, let's have a look at the y's. Okay, so the y's again. So that's negative 0.6t plus 0.1t squared equals 1.1t minus 6. Again, we're going to rearrange that. Okay, so we end up with 0.1t squared minus 1.7t plus 6 equals 0. And again, if I multiply the whole of that by 10, I get t squared minus 17t plus 60 equals 0. That factorises. Okay, and again, it's a show that, so it's important that I do the working out. And from that, I get t equals 5 or t equals 12. Now, that's the important thing, because what you've now got is you've got the same answer in both bits. So you can say, right, as t equals 12 satisfies both equations. Right, the skaters meet when t equals 12. Okay. Right, so in this one we're just going to look at one more. Okay. Right, so in this one I'm going to I'll work in i's and j's for you. Okay, so it says an object moves with constant acceleration so that its velocity changes from 15I plus 4j meters per second to 5I minus 3j meters per second in 4 seconds. We need to find the acceleration of the particle. Okay, first of all. Right, so let's have a little look at what we've been given. So first of all, we've been given our initial velocity, okay, which is 15I plus 4j meters per second. Our final velocity, which is 5I minus 3j meters per second. We know that time is 4 and we want the acceleration. So again, we're going to use v equals u plus at. This time I'm going to do it in i's and j's. So therefore, we've got 5I minus 3j equals 15I plus 4j. And then it's going to be 4a. Okay, therefore 4a must equal, okay, so it's negative 10I minus 7j. Again, I've not put the units on. And if you divide both sides by 4, you get that a equals, well, negative 10 over 4 is negative 5 over 2i. Negative 7 divided by 4 is 7 over 4j. And that is meters per second per second. Right, the last bit just says, given that the initial position vector of the particle relative to a fixed origin is 10I minus 8j, find the position vector of the particle after t seconds. Okay, so we know the initial position vector. Okay, now you've got to be very, very careful. Okay, everything that we have done so far, okay, has been from a starting point. So we've got R equals ut plus a half at squared. Okay, so we've got R equals, now u was 15I plus 4j t, and then it's plus half. Now we know that a is minus 5 over 2I minus 7 over 2j. Okay, and that's t squared. Okay, but that is the position from the starting point. And the question very clearly said, find the position vector. Okay, so I need to add on, I'll do it in a different colour so it really stands out. I need to add on the initial position. It said given the initial position. So we've actually not used that. So I need to add on, and I'll do it in blue so it really stands out, 10I minus 8j. And that is the bit that is often forgotten about. Okay. So I'm just going to sort that one out. I will pull all my i's and j's together. So I end up with r equals. So I end up with, okay, so it's 10 plus 15, 15t. Okay, minus 5 over 4 t squared, and that's in the I direction, plus, and it's minus 8, gives you 8, plus 4t minus 7 over 8 t squared. Okay. Just check that's right. Oops. Yes, I've realised what my mistake is. Somebody was shouting at me. It should have been a 4. My apologies. Okay, and that is in the j direction, and that is meters. So that is your position vector. Okay, so that is the second video using the equivalent of SUVAT with vectors. So if you see something that talks about constant acceleration, but you're given it in vector form, you're given your position vector or so on, okay, you can use these, but again, you've got to be just a little bit careful about position.